All right, we're going to do 3.5 today. The first part of 3.5. Just get your notes out. So 3.5 is graphing rational functions. So we've done some simplifying and solving with these. We've also done a domain of these quite a bit. Now we're going to be looking at their graphs. So a polynomial function is p of x over d of x, where p of x and d of x are polynomials. So to make a rational function, you have to have an x in the denominator. Okay, that's what makes a rational function. The zeros are found from the zeros of the numerator. So p of x and zeros. The zeros come from the zeros of the numerator. Remember, the zeros are the x-intercepts. The domain is found when d of x, when the denominator is equal to 0. That's the values that x can't be. That's the domain. Again, we've done that several times. That's also going to be where we find our vertical asymptotes, but we'll talk about that later. So the parent function of a rational is just 1 over x. 1 over x. Most rational functions that we're going to do will have vertical and horizontal asymptotes. Sometimes they'll have more than one vertical. It's possible that the horizontal asymptotes, certain parts cross those, but definitely vertical asymptotes, the graph never crosses or touches. So these asymptotes here, this is the equation, x equals 0. So vertical lines are x equals, horizontal lines are y equals. So asymptotes are like limits. So the graph will approach those, so they're being drawn closer and closer to them, but they're like a limit, so they can't actually touch it or cross it. All right, so when you draw your graphs, you have to include the asymptotes and draw that your graph is getting close to it, but not actually touching or crossing. So I want to take a few minutes to talk about just some parts here. Just let's practice finding the zeros and the domain. So remember from here, the zeros are the zeros of the numerator, and the domain is where the denominator can't equal 0. Okay. Well, for the zeros of the numerator, when it's just 3, 3, well, there's no way you're going to get 0 there, okay, because you don't have an x and nothing to plug in. So if it's just an integer, just a number, then you don't have any x-intercepts, and that's because there's an asymptote right there on the x-axis. So you can write none or NA. And then the domain is for the denominator. So I know that x cannot equal what? 2. Positive 2 is what would give me 0. So remember how to write that in interval notation. You have negative infinity up to 2, and then 2 to positive infinity. Use that double parentheses to show there's a hole there at 2. Okay, the next one, zeros of the numerator. So I'm wanting to find the zeros of the numerator. Okay, so that would be x equals -1. Good? And then for my domain, I know that x cannot equal -4. So I'll write it the same way as I wrote this first one, but instead of 2, I'm going to use -4. Sometimes you have to factor to find your zeros and the domain. So for this one, I have x squared minus 9 equals 0. So what does x squared minus 9 factor to? Okay, x plus 3, x minus 3, so that means my zeros, okay, 3 and -3. Okay, now domain. So I know that x squared plus 1 can't equal 0. So if I solve this, okay, and I take the square root, what happens when I square root a negative number? Yeah, it's imaginary. So the definition of the square root of -1, and so I should have plus or minus here, is plus or minus I. So when you have imaginary numbers, when we're graphing, those do not apply. So what that's saying is that I can plug anything in for x squared, any real number, and I'm not going to get 0. So, because no matter what you plug in for x squared, you can't get -1 unless you use imaginary numbers. And so we're not using imaginary numbers when we're graphing, we're using real numbers. So my domain here is all real numbers, from -infinity to positive infinity. I can plug anything in for x because no matter what real number I plug in, I can't get a -1 when I square it. And then that means the denominator would not be 0. Okay, let's look at this last one. Alright, so the numerator gives me my zeros. It's quadratic, so I want to factor it. What would I do to factor this one? Yeah, factor out an x. then the zeros, okay, this x out front, what's the 0 then? 0, good. And then x minus 4, 4. Okay. The denominator, so I know that x squared minus 4x minus 12 can't equal 0. So multiplies to give me negative 12 and adds to give me negative 4. Positive 2 and negative 6. Good. So I know x can't equal negative 2 or positive 6. All right, so writing that in interval notation. So I have 2 wholes now. So I'm good with everything from negative infinity up to negative 2. Then there's a hole. And then I can have everything from negative 2 to positive 6. And there's a hole at 6. And then 6 to positive infinity. So remember, domain, you can use a number line to help you if you wanted to make a number line here. So you have open circles here, you have holes at negative 2 and 6, but everything else is okay. So I have 3 parts of this number line that's shaded, that's why I have 3 intervals. Okay? Questions about any of these? So the domain is also going to help us find our vertical asymptotes. Okay? We'll use that more tomorrow or Monday. All right. So standard form of a rational is this p of x over d of x. There's also a shifted form. So today we're going to be spending time graphing things with shifted form. On Monday, we'll be able to graph them in standard form too. Okay, so the parent function, okay, 1 over x. Let me talk a little bit about this shifted form though. So this h and k is like the center of these rational functions. So the point is not actually on the graph, and the h and k is where we get our asymptotes. And so we'll talk about that more in just a minute. But a is an integer. Well, it could be a fraction too. So sorry, it's a rational number. The main thing I want to point out is that it is just a number. So it is not a polynomial anymore. There's not an x in the numerator when it's in shifted form. All right. So again, if we look at that parent function, so there's the center. Okay. The graph looks like this. vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Okay, so let's look at a shifted one. So I'm just going to do shifted in general here. I'm not doing a specific one. So let's say here is the new center. Okay, so this is where your asymptotes will go through that center point. So I'm just going to call that H and K. So therefore, my vertical asymptote is x equals h. So if you look back at your equation, here's x minus h. X equals h is your vertical asymptote. Your horizontal asymptote is y equals k. So this number here. Okay, so I want to write out our horizontal asymptote. So a lot of times I'll just abbreviate that as HA, horizontal asymptote is y equals k. And this is when it's in shifted form. And then my vertical asymptote okay, so I will abbreviate that as VA. That's x equals h when we're in shifted form. Okay, so we're going to practice graphing a couple of these. Okay, so keep in mind that the parent function, the a value is 1. So this being a 3 changes it. It goes in with one of the transformations. So let's rewrite this. Let me just rewrite this here. I'm going to pull that 3 out and write it like this. Okay, and then I don't have anything added or subtracted, so I'm going to put a plus 0 at the end. So pulling this 3 out front, okay, that's the same thing as having a 3 in the numerator. Okay, so this tells me then that the center point HK, so opposite of what's here, so 2, 0. This 3 does not have any effect on your center. But I'm going to use that to help make graph. Okay, so if I describe the transformation, so I'm looking at this here. First thing that would happen would be this minus 2 in the denominator. So that means you're going to shift. So when it's with x, that means you're shifting left and right. It's negative 2, so you do the opposite, shift right 2. The next thing would be your A value here, that 3 out front. So 3 is greater than 1. So that's a vertical stretch or shrink. Good. Vertical stretch by 3. Okay. And then plus 0, that means you're not shifting up or down. So just 2 transformations. Okay, so that's the transformation part. When we go to graph any rational function, no matter what form, we want to go through these next steps. So first thing we want to talk about is the zeros. So go back to your original when you're looking at the zeros. And remember, if there's not an x up top, then your zeros are none. There's no zeros there because there's not an x up top to give you a 0 in the numerator. Okay. We also want to find our y-intercept. So go back to your original and plug 0 in for x, just like we do every time we find a y-intercept. So that's 3 over negative 2. So 0, negative 3 halves. Then you want to find your asymptotes. So your vertical asymptote and your horizontal asymptote. I can go ahead and graph 0, negative 3 halves. So, right here. Okay, so my asymptotes come from where the center is, so that's 2, 0, that point's right there. So that means that here's my vertical asymptote. You should dash these so we know it's not actually points on your graph, but it is needed to show your boundaries, your limits of your graph. Okay, these are lines, so they should be written as an equation. So for your vertical asymptote, do not just tell me 2. This is the line x equals 2. And then my horizontal asymptote, that's the line y equals 0. So remember, x equals h, y equals k. Okay. So then from here, you need to find additional points. So I'll be giving you the graphic calculators because you will want those to kind of help you sketch these graphs to see the shapes. I want, at least on these 2 points in each region. So use your vertical asymptote as a line that divides your graph. So I want to see 2 points to the right and 2 points to the left. So I already have 1 point on the left, so your y-intercept counts as one of those. So if I'm still looking on the left side, so the left part of that vertical asymptote, what's another number I could plug in? So I want to be left. Negative 3? Okay, sure. You can plug in negative 3 because that's left of that vertical asymptote. What else could I plug in? I already know 0. 1, negative 1, negative 2, negative 3. Anything left of that vertical asymptote. I heard negative 3 first, so we'll do that one first. So plug that back in into your original. So that's 3 over negative 5. So that's the point negative 3 fifths. Okay. All right. So I can see the shape here on the left. So I kind of have an idea of what these are supposed to look like. And you have your asymptotes to help you too. You know you can't touch or cross. So you're just going to be staying in this section. Okay, now let's look at the right. So right of that vertical asymptote. So what is a point I should plug in? Or could plug in? What? 3. Okay, good. So then that's 3 over 1, which is 3. So the point 3, 3. Okay. And I need one more to the right. So what's another point? 5. So 5 is a good one because it'll give us a whole number. You could plug in 4 if you wanted. So 3 over 3 is 1. So then I also have the point 5, 1. Okay. So from here you can sketch it. You can also check in your calculator, see what it's supposed to look like. I know it's hard to draw like you're getting close to that asymptote without actually showing that you're touching it. So if it accidentally touches it, that's not a big deal. But if you just blatantly touch or cross like this, you will miss points. Okay? Asymptotes are there for a reason. They do not touch or cross. They get closer and closer, but they don't actually touch or cross. So take the time to draw your graphs the best that you can. Do not cross the asymptote. Okay. Any questions about that? All right. So now we're going to have one in standard form, and I'm going to show you how to rewrite it so it's in shifted form. Okay, so this is not in shifted form. We are going to create shifted form using long division. Okay, so on your test, it will either be given to you in shifted form or standard form, and you could graph in those forms. You will not have to rewrite something like what I'm going to show you here. So this part, just an extension, how we can show we can rewrite this in shifted form. So I know it's not shifted form because I have an expression, I have an x here. Which shifted form only has a number, no x. Okay, so my divisor is x plus 4, and I'm dividing x plus 1. So what do you have to multiply x by to get x? 1. Okay, and then we're distributing. Okay, so that's x plus 4. And you subtract down with long division. So 1 minus 4 is negative 3. So my remainder is negative 3. Okay, so writing that answer out, I have x plus 1 over x plus 4 equals 1 plus negative 3 over x plus 4. So you put your remainder over your divisor. And that is our shifted form. So g of x equals negative 3 over x plus 4 plus 1. So I just switched the order there so it looked more like our shifted form. So our center would be what? Negative 4 and 1. Okay, so if I want to describe this transformation, and you do it in the correct order. So remember, negative 3 is the A value, and I showed you how we can pull that out front. But the first thing is still this horizontal shift. So I'm going to shift which way? Left 4. Okay, my A is negative 3. So when you're looking at A values, the negative is away from the number. So the negative does what? It reflects, right? It flips it. So there's a reflection over the x-axis. Okay, then I look at the 3. So 3 is bigger than 1, so it's a vertical stretch or shrink? No. So the negative does the reflection, and then the number gives you the stretch or shrink. So whenever we looked at stretch and shrinks, we always had to say absolute value of A. Right. So if absolute value of A is greater than 1, it's a stretch. If absolute value of A is less than 1, it's a shrink. So that would be like 1/2 or 1/3. Okay. And then the last thing is that plus 1. So I shift up 1. Good. All right, that's a transformation. Now we need to identify the parts of the graph. So go back to your original. I mean, you'll use this HK, the centered, to write your asymptotes. But for your zeros and your Y-intercept, just go back to your original as G of X. So remember, it's zeros of the numerator. So x plus 1 equals 0. So x equals, yes, x plus 1. So x equals negative 1. So I have 1, 0 there at negative 1. A Y-intercept, plug in 0 for x. Just go back to your original. So that's 1/4. So 0, 1/4. Okay. And then you want your 2 asymptotes. Your vertical asymptote, that's x equals h, so x equals negative 4. horizontal asymptote is y equals k. So y equals 1. So you need to have those equations somewhere. So you can either have them like this at the side where you label vertical, horizontal, or you can write their equations right next to them. So x equals -4. You don't need to do both. Y equals 1. So you either need to identify them to the side or label them on your graph. And they should be written as an equation. So you have to have the x equals and the y equals part. Okay, so now we need some additional points. So your vertical asymptote is what divides your graph. So I have 2 points. Both of those points are right of this vertical asymptote. So I'm not going to find any more on this side. I'm only going to focus over here on this left side. So what is a number I should plug in? Okay, so left of this would be, starting here, is -5. So let's plug in -5. And again, I'm working back. You could plug these in to your shifted form, but the standard form is easier to do this part. So that's -4 over -1, +4. So -5, +4. Okay. I want to have at least one more point over there left of that. So what's another point I can plug in? Okay, -7. You could also do -6, but -7 will give us a whole number. So -6 over -3 is +2. So -7, 2. Okay, so I'm going to sketch the graph in now. So use your asymptotes to help you as well. If you have no clue what these are looking like, use the graphing calculator to help you. Okay, when you type stuff like this in the calculator though, if you use the division sign as your fraction bar, these have to be put in parentheses. Okay. We're not quite done, just a second. Any questions about this? Okay, let's talk a little bit about multiplicity. So the multiplicity with rationals kind of does the same thing as with polynomials. So if you have f of x, your parent function 1 over x, but then you look at x with a multiplicity of 2 here. I'll show you what it looks like. So you have your f of x. This is the parent function. This is the graph of g of x over here. the parent function, remember, looked like this. This is g of x. So it kind of has a bounce, meaning it did not cross and be, hold on, it will be below that x-axis. It bounced and they both stayed above that x-axis. So they're similar to that cross and bounce technique. We'll use that to kind of help us graph these, but really we're going to want to use a graphic calculator when they get big, because they start to get a little bit confusing. Okay. Yeah. So that's the last little bit I want to talk about. We'll do more multiplication.